Hello everyone, this is Felix Baudouin. I am the CEO of Nano Academic Technologies. Due to time zone differences and travel constraints, I'm not able to join this webinar. However, as the CEO of Nano Academic, it is my great pleasure to record this video to introduce our scientific software solutions to the Indian community in partnership with Impulse Technology. In the first part of my presentation, I will introduce Nano Academic, our company and product overview. In the second part of my presentation, I will introduce our vision for technology computer-aided design of quantum devices. In the third part of my presentation, I will introduce the features that make QTCAD unique and the right tool for quantum hardware modeling. Finally, in the fourth part of my presentation, I will introduce use cases that demonstrate the usefulness of QTCAD in real-life settings. So I will start with Nano Academic company and product overview. Nano Academic is a Canadian SME based in Montreal. We have 16 employees, among which 9 PhDs. This involves computational and theoretical physicists, engineers, and full-stack software developers. We were founded in 2007 as a spin-out from research done in the group of Professor Hongguo from the McGill Physics Department. Our main activities are scientific software development and its commercialization, along with scientific consultancy services that we offer to some customers. At its core, Nano Academic is a computational materials science company. As such, since 2007, we have developed and commercialized two main scientific software packages, NanoDecal and Rescue, that address atomistic material science problems. With NanoDecal and Rescue, it is possible to predict equilibrium and out of equilibrium properties of materials from first principles for large systems containing thousands of atoms. More recently, we have developed QTCAD, which stands for Quantum Technology Computer-Aided Design. The main goal of QTCAD is to be able to predict performance of quantum devices before their fabrication and therefore reduce trial and error and accelerate R&D in quantum technology. We have released the first version of QTCAD in May 2022, which addressed specifically spin qubits in semiconductors. And in May 2025, we expanded the feature set of QTCAD to also be able to model superconducting qubits. Now I'll describe the landscape of users and collaborators in relationship with QTCAD. QTCAD users are scientists and engineers working at R&D labs in academic, government, and industrial settings. QTCAD was developed in part thanks to government partners who we want to thank here, who invested in QTCAD through R&D grants. So this involves the Canadian and Quebec government. We are also grateful for our R&D partners and customers in North America, Europe, and Asia. This involves large corporations such as STMicroelectronics in France, quantum startups developing quantum computers such as Equal1, Cobly, Quantum Motion, Semicon, and North Quantic, government labs such as NRC Ottawa, and universities such as Politecnico di Torino and University of Toronto. It's important to note that we have commercial users of QTCAD from both industry and academia since mid-2023. I will now describe our vision for technology computer-aided design of quantum devices. Our vision is best understood by analogy with conventional TCAD, that is technology computer-aided design. TCAD has helped the semiconductor industry to grow since decades, and the idea behind TCAD is to start from an industrially relevant real device, such as a CMOS device or NMOS or PMOS device, create a 3D model of that structure, which can address arbitrary topologies, mesh it, and solve classical or semi-classical physics models to calculate performance metrics that are experimentally relevant to the technologies being explored. For example, for transistors, this is very often current voltage characteristics. In quantum technology computer-aided design, the basic idea is the same. We start from a real device that is industrially relevant, here an FDSOI structure from STMicroelectronics, create a 3D model of the structure, mesh it, but now solve deeper quantum physics problems, so deeper quantum physics models to calculate figures of merit that matter to quantum technology experts. And the key idea is that those figures of merit are much more quantum mechanical in nature. In particular, Very often, we need to account for quantum superpositions or entanglement or quantum confinement, all effects that are less relevant to classical devices. So the key argument here is that while conventional TCAD software is excellent for its purpose, it is not suitable to quantum hardware design. In this context, Nano Academic offers several competitive advantages over conventional TCAD software. First, we have developed our own in-house adaptive meshing algorithms, which enable users to meet predefined accuracy targets. This is, of course, typical from TCAD software. However, in the context of spin qubits in semiconductors, we have several advantages. In fact, conventional TCAD software is optimized for room temperature operation, which makes it challenging to converge nonlinear Poisson electrostatics at deeply cryogenic temperatures below 1 Kelvin. By contrast, in QTCAD, we have developed our own adaptive meshing algorithms that ensure robust convergence at such low temperatures. Our second advantage is the availability of atomistic models. Thanks to Rescue and NanoDecal, we are able to model large, complex material supercells containing up to 10,000 atoms and benefit from some AI acceleration. So this gives access to modeling very small nanometric features such as quantum defects, such as phosphorus donors in silicon or other quantum defects. And perhaps the most important competitive advantage is that we have coded deeply quantum mechanical models for the specific problems that we want to solve, in particular for spin qubits and semiconductors, directly into QTCAD. And this is absolute necessity for accurate qubit modeling. The QTCAD workflow is as follows. First, our users select a relevant technology that they want to model. For example, FDSOI structure that may be used to implement quantum dots or spin qubits, or XMONs or transmons connected by resonators. So any relevant spin qubit or superconducting circuit technology that one wants to model. Second part of the workflow is to define the geometry with the third-party open source software GMesh, which also comes in with CAD capabilities. Once the geometry and the mesh are defined, they can be loaded into QTCAD through our flexible and user-friendly Python API. The Python API is key to the power of QTCAD because it enables our users to automate workflows, sweep design parameters, and optimize them. And it also enables QTCAD to integrate seamlessly in the software ecosystem that gravitates around quantum technologies, which is mostly Python-based. In the fourth step of this workflow, after running a QTCAD simulation, and this is done in the Python script by defining materials or quantum models to be solved, our users can visualize and post-process the results of the simulations using standard Python-compatible tools such as PyPlot, PyVista, or ParaView. It is now time to describe the features that make QTCAD unique. I will start by features that are especially relevant to spin qubit modeling. First, we have developed our own adaptive mesh algorithms to model cryogenic temperature electrostatics. So this is typically done by solving a nonlinear Poisson equation that accounts for charge carrier distributions in reservoirs. And we showed in 2022 in a paper that was published in Applied Physics Letters how this makes convergence much more robust. Second, we have effective mass and K.P solvers to describe the electronic structure of quantum dots at a single electron or single hole levels. Third, we also have many-body and master equation solvers that enable to calculate various many-body physics properties of multiple electron or multiple hole systems in quantum dots, and in particular, compute charge stability diagrams that are used experimentally to identify gate bias configurations leading to the single hole or single electron regimes. The spin qubit modeling package of QTCAD also includes many more advanced features that are needed for specialized calculations that determine the key figures of merit of spin qubits. We have a valley coupling calculation tool based on multi-valley effective mass theory. This is especially important to describe spin qubits based on electrons in silicon quantum dots. We have several advanced spin physics modules, such as spin-orbit coupling, magnetic effects, including orbital and Zeeman effects, and these are coded for both electrons and holes. We can also describe quantum well physics in a hybrid 1D, 3D approach, in which quantum confinement may be described along one direction only, for example, the growth axis, while plane waves are assumed along orthogonal directions. This is particularly useful to describe quantum dots interacting with nearby two-dimensional electron or hole gases. We have modules that describe Rabi oscillations, and this can be used to calculate how fast quantum logic gates can be applied in a single qubit setting. In particular, we have tutorials that explain how to model micromagnet EDSR, which is one of the dominant techniques to implement single qubit gates in spin qubits. This enables to predict Rabi frequency and leakage from device geometry and input magnetic field gradients directly. We also have pedagogical tutorials that explain how to use our single body and many body Schrödinger solvers to compute tunnel coupling and exchange in double quantum dots. This is particularly important to describe two qubit gates in spin qubit systems. We also offer non-equilibrium Green's functions transport package that enables to describe sequential tunneling through quantum dot systems and predict currents arising from this sequential tunneling. Note that this NEGF module can also be used to describe regular transistors, and this is especially useful for cryo-CMOS applications. We have many additional features, such as parasitic volume and surface charges to describe defects in the structure. These defects can even be zero-dimensional through point charge defect feature. We have lever arm matrix solver that is key to describing charge stability diagrams accurately. We have a strain solver, and we also have Jupyter Notebook support, which makes QTCAD usage much more user-friendly. A free 30-day trial version is available online on our client portal for QTCAD 2.0, the most recent version of QTCAD that came out in May 2025. In QTCAD 2.0, we released an entirely new package of QTCAD called QTCAD Atoms. QTCAD Atoms offers a multi-scale simulation framework leveraging the tight binding method. When combined with QTCAD device, this enables to simulate quantum dot systems in two main system scales. First, at the length scale of electrostatic gates, we can compute electrostatics using finite elements, assuming a continuum description of the system. And this enables to calculate the confinement potential throughout a 3D model of the structure. But QTCAD Atoms enables to zoom in on the quantum dot region and model quantum dots with atomistic resolution. This enables to include key imperfections such as rough interfaces or random alloying. And here I'm showing the localized eigenstates calculated in the presence of such a rough interface between silicon, the red balls, and silicon dioxide, the blue balls. And we can see a much more complex wave function than what we would get with continuum model, including oscillations at the atomic length scale. This kind of resolution is absolutely needed for accurate quantitative description of many phenomena that determine the performance of spin qubits. For example, Valley physics, spin-orbit coupling, G-tensors, strain, and this can be used for many applications such as device-to-device variability studies and their impacts on, for example, two-qubit gates or shuttling. Finally, in QTCAD 2.0, we released superconducting circuit modeling features that lay the groundwork of our vision toward multi-scale superconducting circuit modeling. If we think of a typical superconducting qubit chip, it can be described, for example, using a lumped element model in which various components like capacitors and Josephson junctions are parameterized through quantities like capacitances, inductances, and Josephson energies. These parameters determine the Hamiltonian of the chip, which can itself be solved using open source software such as QTIP or SC-qubits, leading to the calculation of key figures of merit of performance of those chips. However, to calculate those parameters like capacitances, inductances, or Josephson energies, a description, a more fundamental description of the component is needed. And this fundamental description can be done at different length scales. At the length scales of classical components, one is interested in, for example, capacitances, uh, frequencies of Maxwell eigenmodes, coupling strengths, etc. And these are typically captured by finite element modeling software that are used conventionally in microwave engineering. And we're proud to announce that QTCAD now supports these features. And starting from QTCAD 2.0, it is possible to compute capacitance matrices and Maxwell eigenmodes using QTCAD. At the most fundamental level, however, it is important to calculate the Josephson energy of Josephson junctions. Josephson junctions are the key component of superconducting circuits that make quantum computing possible. And it turns out that Josephson junctions are so thin, just a few nanometers, that each atom can influence the transport through the junction. As a consequence, we have recently leveraged our atomistic simulation software, NanoDecal and Rescue, to describe Josephson junction properties from first principles at the atomic scale. That I have introduced the main features that make QTCAD and nanoacademic software unique, I'm happy to introduce use cases of such software that demonstrate usefulness of our offering in the quantum technology setting. In this first use case description, I will describe how the spin qubit startup Equal One benefited from QTCAD simulations in its modeling of Global Foundries devices. Recently, Equal One published this preprint on the archive in which they demonstrated double quantum dot behavior in a Global Foundries 22 nanometer FDSOI device. In this preprint, Equal One describes quantum well formation in the structure. Compare experimental results with QTCAD simulations. In particular, Equal One studies the lever arm of the quantum dots obtained in these structures. The lever arm indicate by how many electron volts do single particle energy levels in a quantum dot shift when applying 1 volt of gate bias voltage. And it turns out that quantitative agreement was achieved between QTCAD simulation and experimental measurements within a few percents. Equal One authors argue that this demonstrates the feasibility of simulating quantum properties of quantum devices in commercial semiconductor structures prior to fabrication, which will guide their designs in the future. Recently, Equal One commercialized the Bell One machine, which is a rack-mounted quantum computer that can be plugged in a standard 120 volts outlet and integrates in data centers. I'm showing here a picture of this device as demonstrated at the exhibit hall at the APS March meeting in March 2025. If you were to zoom in the fridge that's shown in this picture, you would see a chip, and that chip was studied in the preprint whose link is given here. It's an archive preprint. And in the inset of this figure 1 of the preprint, we can see a diagram which shows the conduction band edge throughout the structure, the sextuple quantum dot array that is used to implement the Bell One machine. And this simulation was done with QTCAD, which demonstrates how QTCAD modeling can help understand chips that are actually put in present-day quantum computers. In use case number 2, we demonstrated atomistic modeling of a dopant quantum dot in collaboration with McGill University by combining DFT calculations done with Rescue with QTCAD's many-body solver. I'm illustrating here a silicon supercell. It's a cube of 6 nanometers by 6 nanometers by 6 nanometers that contains roughly 10,000 atoms. In the middle of that cube, one silicon atom is replaced by a phosphorus donor. And we calculate the charging energy of the dopant quantum dot that is formed by bound states of the phosphorus donor in silicon. And we calculated this charging energy completely from first principles for the first time by injecting Kohn-Sham orbitals calculated with rescue into QTCAD's many-body solver. And this approach led us to a charging energy that was very comparable to the experimental value, completely from first principles without any experimental input. We also plotted the two-body wave function of electrons bound to the phosphorus donor, and this was deemed interesting enough by applied physics letters editors to put it on the front page. In use case number 3, we describe various finite element modeling calculations of superconducting circuit components done with QTCAD recently with collaborators, in particular at North Quantic, a quantum startup based in Sherbrooke near Montreal. With North Quantic, we demonstrated capacitance matrix extractions of a transmon in a cavity and compared with reference values to show quantitative accuracy, and also validated performance with North Quantic engineers to ensure that this met their performance requirements. We also demonstrated capacitance matrix extraction for an X-band qubit and calculations of Maxwell eigenmodes for meandered resonators. It's important to highlight that QTCAD integrates seamlessly with Qiskit metal, enabling workflows in which Qiskit metal is used to produce chip layouts, and QTCAD is used in the backend to compute properties of those layouts. In use case number 4, we show how nanodecal was used for first principles modeling of Josephson junctions. We show here how we were able to successfully relax at the atomistic model of a Josephson junction. And using this relaxed structure, we plot the electrostatic potential along the transport direction for two oxide thicknesses of the junction. It's also important to acknowledge that the termination mode of the junction, that is the configuration of atoms at the interface between aluminum and aluminum oxide layers, has a huge impact on transport. And this is what we illustrate in this slide. The electrostatic potential first is very different in both cases, and the atomistic description of the electrostatic potential shows features that are much more complex than typical square potential barriers that are used to model Josephson junctions. We can plot the transmission function for two termination modes of the junction and see that the transmission, in particular at the Fermi level, can be orders of magnitude different for different termination modes. We can plot the Kohn-Sham orbitals of electrons scattering through the junction and see that in one termination mode, electrons easily go through, while in the other, they are reflected back into their original side of the junction. These calculations are particularly useful to compute properties of Josephson junctions. Using the Ambegaw-Karabarata formula, it is possible to relate the normal state conductance of the junction, which we calculate with nanodecal, to the Josephson energy of the junction. And in this table, we compare our results with the results from the literature and experimental results, which shows that quantitative agreement can actually be achieved between nanodecal modeling of Josephson junctions and these reference values. These were only very specific use cases that I found particularly interesting for this audience, but there is an ever-growing list of publications using QTCAD for scientific research and device engineering. Some of them come from NanoAcademic itself, but there's a growing list of publications from our users that do not involve NanoAcademic researchers. And stay tuned, we have this list here, and the list is growing. It doubled since last year. Finally, I would like to take a few moments to introduce QTCAD EDU. So far, I have focused on use cases of QTCAD in research context, in industry and academia. However, there is increasing demand for QTCAD in an educational context. The reason is that there are many projections that indicate that there will be a critical workforce shortage issue in the quantum industry, which is growing very fast. And to meet to address this challenge, one potential solution is to train engineers in quantum hardware design, in addition to our traditional physicist-centric workforce. Why QTCAD EDU can play an important role here is that engineers are typically very accustomed to using CAD or TCAD software in their work, and QTCAD EDU enables to put professional grade quantum TCAD software into the hands of engineers while they are being trained in universities. And so QTCAD EDU is a licensing scheme that is especially adapted to classroom usage of QTCAD in context of professors teaching quantum hardware classes to students at master's degree or advanced bachelor's degree courses. We can highlight some use cases of QTCAD in education. For example, Politecnico di Torino is giving a class on quantum hardware design for the second year this year using QTCAD. And recently, University of Toronto started giving a quantum technology class in its electrical engineering department, in which QTCAD is used for both spin qubits and superconducting qubit modeling. With this, I would like to conclude and pass the mic to Impulse Technology, our distributors in India. We are extremely excited to introduce our quantum hardware modeling solutions to the Indian community as it pushes forward for the development of quantum technologies in India. Thank you very much.